Should be good.
What? So quickly.
That's yeah. Yes. Well, they're paid. Sorry. They do want to see.
Good morning. Here we have the exam on Thursday, and I was talking to a few students yesterday, those who are enrolled in the tutorial section for this course. And based on the feedback I received, I changed my plans and I'm going to do review for the exam today. Basically, that means that I'll go over one of the exams. Probably we will have time for only that, unless you have some suggestions for me. I plan to go over the exam from last year, same semester last year. And that doesn't mean that these questions become important. That's not what it is. This is just so that you probably have studied by now a little, and this sort of reinforces what you're studying. So that's the goal. What I'm doing doesn't mean that this becomes more important for the exam in any way. Again, the priority for studying for the exam is lecture examples, homework examples, and textbook examples. What I do today, it might help in the sense it's me who has made this exam last year, and it's probably the same influence I might have in making the exam. In that sense, it might be. Okay, any questions on that? So we have midterm exam. And again, the expectation is that there might be anywhere between 7 to 10 questions. About 40% of some conceptual. 60% homework like. What does it mean to say it is conceptual? By that I mean, while doing a proper homework problem, there are a lot of concepts that come together to make you do that problem. I'll pick one small piece out of it. For example, the difference between a conductor and insulator plays an important role in many analysis in most of the problems. So and it is a concept that inside a conductor, the charges are free to move, that means to say electric field is zero inside. In fact, there is no electric effect inside a conductor. And insulator, the charges are absolutely not free. We are talking in the extreme sense where the perfect insulator and perfect conductor. So that plays an important role in deciphering the problem and doing a particular problem. And that becomes a concept that I can use that in a, where if you know the answer, it might be just 1 minute. Typical questions I've asked in the past is, what is the electric field at the center of a perfectly conducting sphere? It is zero. What is the electric field at a distance halfway between zero and the circumference of a sphere? Again, it is zero. Anywhere inside a conductor, it is zero. Rest everything is irrelevant. If you're inside a conductor, electric field is zero. Not necessarily for a sphere. Sometimes in a, sorry, not necessarily for an insulator. Sometimes in an insulator, if there is a lot of symmetry, same thing can happen. It can be zero inside, but that's not always true. So that's requires some amount of, again, more concepts are needed for that. So that's to point out what I mean by conceptual. Statistically speaking, I found that conceptual questions comes out easy for good students, and by good students I mean those who are already getting an A, who have been working on the homework and so on. That's, I believe that's how it goes. It's not necessarily mean a lot of weight should be put on that, but that's how I see the grade. So I don't depend on it too much because it really divides the grade into two, because conceptual questions hurt those who are really not working. And I don't really want to make that the disparity between that too much. So I try to balance that, but at the same time, I don't understand how these things work so much, even after having so much of statistics. So I try, but then I do a lot of curving also to balance out whatever I mess up during an exam. Okay. So okay, so that's, any questions? Anything related to that? Question? Comments? Okay. So I decided I will go by the last year exam. Is there any strong suggestion that I should go? Maybe all of you guys are going to plan to do anyway the last year exam. Maybe here I should do further back in time. Does it help, or last year is better? Last year, okay. So that is. So if you're not aware, this is the course webpage, in the sense a lot of things are available there, and all the old exams that I have made, they have all been made available at this time. So that should be sufficient exam to work with, if you think that helps. Not everyone. I noticed that many people work differently. Okay. So it was a 75-minute exam, and there were about 10 problems in total, 5 conceptual and 5 full problems. But this time probably it will be less. So 4 plus 4 or 4 plus 6. That's how it can. How do you differentiate between a conceptual problem? When I'm designing it, it's a conceptual problem of 5 points, and the other is 10 points. And this format will remain the same. There will be about 4 5-point questions and about 4 or 5 10-point questions. So 2 positive charges and 2 negative charges are placed on the corners of a square. Each of the 4 charges is of the same strength. When the charges are let go, the charges tend to move inward. It means do all 4 of them come inward, or they explode. So let's see this. So this is problem 1. You have 2 positive charges and you have 2 negative charges on the side. Based on the interpretation, you can draw positive here and negative here, that's okay, but diagonally opposite are of the same kind. So that's given, and this is a square, let's say, of length L. These two are positive charges, so they repel. So they repel, first let me begin with this track. So, this track. Let's say that's of unit length 1, and that depends on this force F, depends on the magnitude of the force, depends on K, charge Q, let's say Q square, Q, over the length between them, let's say this is length L, so that's length square, length L. So let's call that F if you want. So that's F. The same force of attraction is there between these two. That's F. If this is of this length, this is exactly of that same length. Now, when it comes to these two charges, they repel, they are the same charge, but now you have to find out what is that force. It's the same charge, so numerator stays the same. The denominator is no more L, right? It is a diagonal. This is a diagonal there. If this is L, that's the side, same side. So this becomes square root of 2 times L. So this quantity here, because there is a square root of 2 times L squared. So let's call this F. FD, let's say. FD diagonal is equal to the same numerator, K Q squared. This is square root of 2. When it's squared, this becomes F over 2. So the main idea is that the diagonal force that is acting is weaker because it is farther, and since it is a squared quantity, it is even made smaller. So it would have been a 4, but then you take the square root of 2, so that made it small. So this is F over 2. Now I can replace this with F over 2. This is not going to balance these two. When these two come together, there is a balancing act there. So let's see what that is. So this is F over, this is F cosine theta. But F cosine 45 that comes in plus F cosine 45. That's the component in here, that's the component in there. And these two have to add up. That's equal to 2 times F cosine 45. And cosine 45 is 3 times F root 2 over 2. 2 cancels out, that's square root of 2 times F. Either you see this visually or quantitatively, you have to realize that this contribution on this side, which is coming from the two components here, these two balance out. This is larger than this. This is square root of 2 times F, that's about 1.4, and F over 2 is 0.5. So this is the pulling that these two are doing is larger than that. You can see that visually itself just by seeing that this is 1, and then on the half of that. Or you can do this quantitatively if you really want to convince yourself very much. And the rest of the arguments remain the same. Now what you're showing is that effectively the total force, total of this is on this side, inward. The same argument goes in here. This is attractive, that's attractive, these two repel. Everything goes through the same. There is a total force in here, which is inward. The same thing in here, inward, same thing in here, inward. So if you let them go, they are all attractive, so they implode instead of explode. This is the quantitative part, but if you just say imploded, if you're not guessing and you have a reasonable argument to that, that's sufficient. Typically, I don't look for the argument in it, but the way it goes is that if you're guessing it, then you don't have a choice, then you just guess and you decide that you get it correct. But if you have an argument, do try to give the argument in the sense, if by any chance it's the wrong argument, you get partial credit. There's a lot of partial credit in the problem. If your argument made sense and you make some small mistake in your argument, you'll at least get some partial credit. All the questions do give the logical thought you're putting in that is basic to most of what you're doing. So what I typically grade the exams, I look for places to give points. I would like to give points, but if it's an empty page, I just cannot help. So try to put some thought in it. Doesn't mean that you just write your equations down, but if I see that you're putting some thought, try to make points. Helps? Any comments, questions? Yes, please.
Why don't you do the f cosine 45 plus f cosine 45 with that sign?
Yeah, so it is, okay, so this is slightly different for typically what I do. So this is your f. And that's your x. And this is your top right now. So this is f over 2. Now, typically the way we proceed is that we break this everything into x and y components, and that's how you do it. But I know that this is the diagonal line that I will be interested in. So I'm breaking it not along these two lines. Instead, I was just looking at this one. So here, the component would be this component here balances this component here. This is being pulled in this way, right? These two balance out. And this component here is f cosine 45. Does that make sense?
Yeah.
If it doesn't, let's do this very quickly in the standard way that I would have done in the class. So that's f. Maybe in the standard way is much easier, right? So this is three forces. The first one is f times I plus 0 times j hat. Second one is 0 times I minus f times j hat. And the third one is f over 2 times that is a cosine 45 cosine 45. So that's root 2 over 2 I hat plus f over 2 times root 2 over 2 times j hat. Total force, we are just looking for the magnitude, so you add them all up. So it is f times 1 plus 1 plus, is that correct?
I think that's going to be a minus and then either.
This will be minus, yeah, thank you. So this is better now? Okay, thank you. Yeah, I was thinking wrong, yeah. Thank you very much. So this is 1 minus root 2 over 4. I have plus, I guess, so plus, now minus again, so this time f 1 minus root 2 over 4. And j. I'm interested in the magnitude. Both these quantities are the same. When they have the same components for both, it is just square root of 2 times whatever component it is. So the magnitude of the total force will be root 2 times f times 1 minus root 2 over 4. And we are asked in what quadrant it is. Actually, you don't even have to do this. You just have to look for which quadrant is this. As a positive number, negative number, the total force will be in this quadrant, right? So that's at total. Is that argument clear what I said?
Yeah.
Right, so this is positive, that's negative, so that's in the fourth quadrant, which means that the total force is here. Which means it will improve, right? It is towards the so that always works, but I thought of when along getting off. Yeah. Hopefully it was not too confusing. Any other comments, questions? Okay. Is that readable? What is the magnitude and direction of the total electric force on an electric dipole when it is placed in a uniform electric field? Right, so the main concept here is that you should know what dipole is. Electric dipole is problem 2. Electric dipole is two charges, one is positive and one is negative. And they have the same magnitude but unequal signs. One is positive, one is negative. Its dipole moment is from the negative to the positive, but let me not worry about that. Therefore, in this question, what is important is that electric dipole constitutes two charges. One is positive, one is negative, but they're exactly the same charge on it. I'm placing an uniform electric field on it. Uniform electric field is like this. The equidistant line means that it is uniform, it doesn't change, there is no intensity difference. If it is 5 Newton per coulomb here, it is the same 5 Newton per coulomb everywhere. So that's your electric field. The force on a charge due to the electric field is charge itself times the electric field. It's like gravity. If it was force on gravity, mass times gravity, G, right? Here it is charge times the electric field. Electric field is the version of what gravity is for a mass, but it is uniform electric field. So E is going to be the same. Positive charge flows towards the charge, flows along the electric field. That's the concept. And the negative charge flows against the electric field. And the amount of the magnitude of the force is charge times electric field. So this will experience a force Q times E in this direction. Let me say just the magnitude. And this one will experience a force in the opposite direction, Q times E. Since the charges are the same, since the electric field is the same, both are exactly the same. What the total force, this plus this cancels out, that total is 0. So it doesn't move. Right? An atom typically is neutral, so if you keep it in an electric field, most of the time nothing happens. Electric field during lightning, there is a lot of electric field in the air. Most of the atoms do not care, but that doesn't mean that it doesn't get affected at all. If this was not straight, to think of these charges being in this position, then the same forces will look like this. Now, what does it try to do? If you had an object like this, think of a dumbbell, and you pull it in this form, what will that object try to do? What will happen to the object? It will stretch, yes, but more than that, it will rotate. Right? That is, so these two components now cancel out, but this tends to rotate the object. So atoms in an electric field do not move around, but they rotate. And they align with the electric field. So that's what happens to the atom. But that's not what is asked in the question. Question is just asking what is the total force on it. That's 0, and that is all that is relevant. In lightning, there is something more happens. It is really getting pulled. So this is the situation here. It is really getting pulled, and this force that is keeping it together can break. And during lightning, they really break. That's called the breakdown of air. Because all the atoms, they are not able to sustain that force. So beyond a certain strength, electric field atoms actually break apart. That's what we see as light. So all the charges really move and separate into positive and negative. They move towards the two plates, if you want. One is the cloud, and one is the ground. Questions, comments? Draw the electric field line for two oppositely charged parallel conducting plates with uniform charge distribution on each plate. So that's problem 3. So plates, one is positively charged and one is negatively charged. Remember, lines, electric field lines always originate from positive charges or from infinity. That's only 2 options. They always end on an negative charge, or they end at infinity. Here you have lots of positive charges. They keep never ending. That's on both sides. So they all start from here. And the concept is for you to realize that they are uniform inside the points. That involves integration, that involves calculation, and that's a message I expect you to have gathered from the homework and all that. Between two parallel plates, electric field is uniform. It's the same idea as why the gravity is uniform, 9.8 meters per second square, right on the surface of Earth. We are so close to Earth that it is to 2 significant digits. It's good to approximate Earth as that flat. That's why most of the experiment where you try to prove that Earth is not flat, you have to go precision experiment. You have to go into the 3rd digit. So in the past, there were difficulties with that, but now it is very easy to realize that Earth is really wrong. So we just, this was the only thing needed, that electric field line between the plates. You also do experiments related to that, so probably this comes out reasonably okay. That is how I look at it. Any questions or comments? Okay. 3 identical conducting spheres ABC carry equal charge. They are separated by a distance much larger than their diameters. Sphere C is first attached to A, then to B. As a result, what is the charge on A? Notice that this is a conducting sphere. That means when I touch the two spheres, they can move around each other. If I change this question to insulating spheres, things change, the arguments change. So let me go over it. Problem 4, we have 3 conducting spheres, A, B, and C, and they're carrying equal charge. Let's say plus Q plus Q plus Q, and that's A, B, that's C. Here C is first attached to A and then to B. So let's go at the first step. So first it is attached to A. So C is attached to A. They become QQ, and then it is attached to B. 3 identical spheres carry equal charge. They are separated by a distance. Well, it's the same. Okay, so it is a different. It changes. So A plus C. So you bring A to C. So what happens is that now charges can be shared between them. So total charge on this is QQ. They can move around. So all the positive charges and negative charge or positive charges stay far away from each other. And you again, when you separate them, again it is. You add the charges and then you separate them. So it is Q itself. So this is plus QQ. But then when I separate them again, A and C again, this is Q plus Q divided by Q, which is again Q itself. Here it is plus Q divided by Q, plus Q again. So the situation has not changed from this, just because we brought in a charge and text particular does not change. It would have been different if this was charge Q1 and then was charge Q2. If they were not the same, they will make it the same. So by catching two conducting spheres, what happens is that the charge becomes equal, it's the average of the field. In this case, it does nothing because it is the same charge itself. So that's just the construct of the system that made it trivial in a sense. But that is now the situation. I have only touched A and C, but next you want to touch then to B. So now you want to touch C and B. Again, it's the same. So when I do the stretching, it is Q plus Q over Q here, and you take it back again, or Q plus Q, not shared yet. So this is C, so this is Q plus Q over Q, so that's Q itself. That's Q plus Q over Q, so that's Q itself, and A stays the same. So nothing happens just because we test two times, nothing happened, so not a very illustrative question, but that's what it is. Any confusing by any chance because nothing happened? Yes, please.
My question was, you have three orbs with three spheres and you put all three of them together at the same time, and then you remove one of them. Your total charge is 3 for 3Q, but you remove one from the three touching bodies. Would you then have a 1.5 Q charge?
Good point. So let's see. Probably not. So let's see. Yeah. So okay. So your prediction is good point. So let's say this was originally Q. So it came with Q, and now you're touching this. Three. So this is Q originally, and that was Q original. Now you have 3 times Q charges on this. And remember, the goal is that you want to be as far as possible. They're free to move, and charges try to stay as far as they are light charges. They stay away from each other. And yes, the configuration will be plus Q will stay in that corner, and another plus Q will stay in this corner, and this will stay in this corner. Now, if you move this again, so yes, so this Q will stay exactly the same, and so there will be Q there. There will be 2 times Q there, and then again you move this, it comes out the same. I was wondering maybe this will be Q 1.5 and 1.5. So it's not, so physically they are really trying to stay away, and then you move it around, it works out better. So I think that makes the diagram makes it clear. Okay, good question. Yes.
You said if it was insulating spheres, it'd be different.
Yes.
What's the difference?
What will be the difference? So let's say there was plus Q here, let's say plus Q1 here, and let's say plus Q2 here. Okay. You bring them together. If it was connecting, they will share. They will just make it average on both sides. But remember, insulating means our definition is they cannot move. So they cannot move from one to the other. You touch them and take it again, it's the same, nothing happens. So insulating, nothing happens just because you. Again, perfectly insulating sphere. Here we are only talking about perfectly insulating sphere. Often there are materials where you can induce things. Often you will see most of the demonstrations that you're inducing a charge. So they are not perfect insulators. You can actually move things a little bit. It's neither a perfect insulator, neither a conductor, and you can have a lot of features coming out of that. But we are not going to work with that just for simplicity. Okay, so I think I answered the question. Yes, please. They weren't equal charges inside and in for insulator. They weren't equal for Q1 and Q2, yes. So plus, so this is insulator, so this is Q1, Q2, you bring it together. Right, so this is now Q of them. So the total charge on this is Q1 plus Q2. Now they are free to move, so they stay separate. How much ever they are, so there's a little bit here, little bit there. How much of them? It's exactly Q1 plus Q2 divided by 2. And half of them will stay there, half of them will stay here. And now you separate them exactly 2, so this will come out to be Q1 plus Q2 over 2. And this is Q1 plus Q2 over 2. Is that a question? Now, maybe the concern is, since the question was raised, intuitively, you might wonder that what decides the distribution of these charges. Notice that there is a language in there saying that they are identical spheres. And that makes sure that this is equal. For example, this configuration here, it was necessary that they make this perfectly symmetric situation. If one was really small, then that is not really obvious. And we will address that question next week. Once we have energy configuration, we will see that most of the charges tries to stay on the smaller sphere. If you notice, have you ever put a fork inside a microwave? Okay, if you're not, I will recommend putting it. Be careful, it creates sparks, but taking this course, go ahead and do it for 3 seconds. Don't do that for more than 3 seconds, but I'll recommend you to do that. First, do a fork and then a spoon. Okay, you will notice that there's a good chance that nothing will happen for a spoon, but in a fork, there will be a lot of sparks. That's because forks have pointed corners. Pointed corners means sphere, like on the surface, it is spherical. Very small sphere, lot of charge. There's lots of charge there. So charges try to stay on smaller sphere, but that's not obvious at all at this point. It should not be obvious unless you're aware of a concept that will come next week. Energy consideration will demand that there is more charge. Energy will remain the same, but there will be more charge on the smaller sphere. That's why you get static electricity on your fingertips, on your elbows. These are all corners of your body, right? On a corner, this happens more. Right? If there is a lightning, don't be close to a corner. Stay away from corners. Like where electricity, stay away from corners or metallic corners. Insulating corners, I would say. So that's just that simple. Okay. Yes.
Yeah, I think in the homework we had a question like this, except we said A and B were positive and C was neutral.
Yeah, then you have 0. A and B is positive, plus Q is 0. So this is 0 now, right? Now you bring this closer, the average it out Q by 2, Q by 2. Right, this now becomes, this is 0 now, right? So this is Q by 2, and it becomes Q by 3. That's clear what I'm saying? And then once it's Q by 2, again, you just bring Q by 2 to Q. Again, they stand, so this becomes 3 by 2, and that is becomes 3 by 4. So you can do that in various ways. So that has all the concepts of an insulator and a conductor, but algebra is very straightforward. So typically, I like to give these problems because it's a basic concept, and the algebra or the background needed is very minimal in there. But I'll change, of course, the configuration. Now that there are 3 charges that have come in the discussion, I can bring in 3 together. So something like that. Okay. Okay. Positive charge Q is placed at the origin. What is the total electric flux passing through a Gaussian spherical cell consisting of a sphere of radius 1 centimeter, enclosing the positive charge completely? This is Gauss's law, problem 5, I suppose. This is related to Gauss's law that says that if you have first concept is that positive charges are source of electric field. That means electric field start from here and go into the negative charge. That's pretty much like water flowing. This is the source, that's the sink. This is the source of electric field instead of source of water. Source of electric field, sink of electric field. We have only one charge, and that's at the origin in the problem. That's the situation, and there is a sphere. We are asked to calculate the flux across. By flux, we mean how much electric field is coming out. And the theorem is that how much flux is coming out of a charge is equal to the charge itself. Up to a scale, that's it. So the only thing you have to do is count the number of charges inside the sphere that's given to you. It doesn't matter which sphere it is. You just have to count the number of spheres. Rest everything is irrelevant. The radius is equal to 1 centimeter, that's irrelevant number. What is important is that the total flux. This is how much electric field is crossing an area. If it's a closed area, it's necessary that it is closed area. That's equal to, so this is closed for a closed surface. Only if it is closed, that is equal to the Q enclosed divided by epsilon naught. There's only one positive charge in there, and that's given to be 8.5. So this is 8.85 into 10 raised to minus 12 coulomb is given to you. And the epsilon naught happens to be exactly that constant. So the number has been given so that it cancels out exactly. And it has units. It has the unit of coulomb square over meter square times newtons. But even if you don't know the unit, the flux is electric field times area. It is Newton per coulomb over meter square. These two cancel out. So that's equal to 1. This is plus 1. And the unit is either we convert this. So this is Newton per coulomb times meter square. It goes in the numerator, Newton per coulomb times meter square. Even if you don't remember this unit, use the left hand side to get the unit. Unit, you should report numbers with units. Is that clear? Whenever it comes to flux, flux is a measure of how much electric field lines is coming out. That depends on how many sources are there inside the volume. It's like how many taps are inside a building, decides how much water is going to come into the building. So you just count the number of positive charges. If it is a negative charge, it's -1. If there are 3 positive charges inside the sphere, you have to count all of them. Only the enclosed one. Outside, you just don't count.
If there's multiple inside.
If there are multiple inside, for example, if this was the Gaussian sphere, and there was +1 here, +1, +1, +1 here, and -1, -2, +2 here, ignore all of them, +1, +1, +1, add them. So you add the ones, or add all the charges, like Q1 plus Q2 plus Q3, all the one that is enclosed, not the one that is outside. Okay. Yes. Epsilon naught is a constant. That's the property of a vacuum. This is like, for example, in the first semester we had 9.8 meters per second square. That doesn't change under the same planet. This is a universal constant. It's the property of vacuum. It is 8.85 into 10 raised to -12 Newton square. Newton equals square. This is just a number I gave so that cancels that. That's just for convenience. I gave it. If it's another number, you have to really do the math. For example, if I tell you 1 coulomb here, if I tell you 1 coulomb, then you have to do 1 divided by 8.85. So epsilon naught is just that. And that depends on which units you're using, and we have been consistently using SI units here in this course. then SI units at say 0.85. Certain units at 1. So if you use Gaussian units, that quantity is 1. That's just for information, but that's not going to be with that. Okay. Okay. So all the 5 charges, five questions that we did until now, they were conceptual questions. Now we are coming into the homework-like problems, which probably will require a little bit of description and going into the details. Okay. 4 identical charges of equal magnitude Q are placed at the corners of a square of length L. Determine the magnitude of the Coulomb force on one of the charges. From 6. 4 charges on corners of a square. Before I start, how many of you prefer conceptual over homework-like problems? Can you raise your hands? Pretty much half. More than half actually. So you prefer conceptual questions, the ones that we have done. Okay. We'll see. Okay. Well, again. Okay. So Q. Just for I think it is clear, it's going to be clear which forces are from which ones. Let's have, like whatever we did here, let's have just a constant here, that K and Q square over L square. That L is the length of this square. So all sides are the same. Diagonal will be square root of square root of 2 times L. These two repel each other, so this will be a force F. Right? That will be exactly this force. So there's a vector force F on acting onto the left. This also repels, so exactly the same length, but acting vertically up. Same force F here. Let me give labels 1, 2, 3, 4. So this is F2, F4, and F3 now will be not having the same magnitude. Its distance is farther. It's not 1 times length L, so it is square root of 2 times length L, but you square it. So the magnitude of F3 is equal, so magnitude of 3, I'm going to point out is that exactly half of this length. It is K, charge remains the same, Q square divided by the length is square root of 2 times L square. That's because if you have here an L, so this is L square plus L square. So it is 2 times L square, and then you take it square root of 2. This is KQ square over when you square it, that's 2 L square, which is exactly F over 2. So once you realize that this is significantly smaller, what are this angle? This is a square, so this will be 45 degrees. That's 45 degrees, so everything is 45 degrees. That's 45 degrees. The idea is to add up all these forces, find the magnitude of them. So F2 is equal to minus F in the I direction plus 0 in the J direction. F3 is equal to F over 2 minus F over 2 times cosine 45 in the I direction plus F over 2, it's in the second quadrant, times sine 45 in the J direction. Sine 45 and cosine 45 are both exactly the same. It is square root of 2 over 2. So this is equal to minus F, this is root 2 over 2, so that's root 2 over 4. I have plus F times root 2 over 4 times J. F4 similarly. It's 0 I have plus F times J. Total force is the sum of all of this. And total of the vector. You add these quantities, so that is minus F. And that is 1 coming from here. This is the same. This is a 0, and this is 1 plus. That minus I've already taken out. So it's root 2 over 4. Right. And I had direction. Same thing comes here, but except that this is all positive. It is the second one, it's 1 plus. Any questions until that? That's your total force in component form. The question asked, determine the magnitude of the Coulomb force. I can also ask what is the direction of this. But this one, if you were to draw, okay. So you have a negative number here, but these two are exactly the same. Right, whatever that quantity is, that's exactly the same amount on this side and that side. It's in the second quadrant, but exactly of the same length. That means that when I add down this quantity plus this quantity, the diagonal will be square root of 2 times that quantity. But if you do not want to use any trick, just mechanically do it with the square root of minus F squared, so minus F times 1 over root 2 over 4 squared, right? Plus F times 1 plus root 2 over 4 squared. Square F, so this is F squared, 1 plus root 2 over 4 squared, but that's exactly the same, so it is 2 times that. It's this plus the same quantity, so it becomes 2 times that. When I take it outside the square root, this becomes the root 2 and F, and this is 1 plus root 2 over 4. So it's the same quantity, just you multiply by square root of root 2, that's because it's the diagonal of a square. Okay. So that's the answer. And now you can simplify it if you want. You should put back whatever F was that we wrote down. It was k3 square over L square. And so the answer would be root 2 times k3 square over L square times 1 plus root 2 over 4. If you want, you can convert this into a number. If charges are given, length is given, you could put all that into a number. If it is an algebraic question in terms of variables, you can leave this as it is. That's perfectly fine. Christian? You have two charges, one is Q1 and the other is Q2, both are positive. Q1 and Q2 are positive. So Q2 is +4. And it's going to 2 civilians. Okay, so the question is, where is the electric field or the force intervals? Where is the total electric field 0? Everywhere along this line, there will be an electric field. For that matter, it's not only along this line, it can be on the y-axis, it can be on a diagonal. Everywhere there is an electric field. But the question is asking only about the horizontal line connecting these two charges. So let's say this is x somewhere. Let's say this is 0. That's your x. So that line is x. The total distance, center to center, let's say d. Notice we want to cancel the electric field. Electric field due to 1 will be away from here, so that's E1. And as we get closer, this gets larger in size. Electric field is larger as we get closer to a charge. For this chart, it is in the opposite direction, but I'm not talking about any the center of anything. That's E2. And we are asking the question, where does it go to 0? So here there is a chance that these two vectors can balance. Where exactly it will balance that is decided by how big they are. Since this is smaller, this is weaker, but as we get closer, sometimes this will get larger. As we get closer there, even though this is larger, because the distance is getting larger, that will get weaker. So somewhere this will balance out here. Exactly where, that's what we are asking. You could ask, what about here? If it was positive and negative, these will not balance here, it will be on the right or to the left. So first you have to figure out where does it balance. Down here, this is E1 is on this side, and E2 is also pointing in this direction. There is no way they will balance on the right if they are both positive. If one was positive and one was negative, they won't balance here. Instead, they will balance on the right or left. So first you have to decide for which side does it cancel out. Here, again, this will be E1, E2, they don't balance out. Okay, so the only possibility is in the center. From that point on, proceed. And since they are going to be balancing, let's say we only need magnitude, right? So magnitude of E1 has to be equal to magnitude of E2. We have already used the fact that they are in opposite direction. Magnitude of the electric field is K times Q1 divided by distance from the observation point from the charge. So that's x squared. And second electric field is K times Q2 over B minus x whole squared. The idea is that numbers are given to you, even capital D is not given. as a multiple of this, so the answer has to be given in terms of d. So this is a known variable in a sense. X is what you're trying to solve, but everything else is given to you, but you want to solve it in terms of d. This is a quadratic equation in principle. If you do not, if you have not practiced this or if you have not encountered this before, it is okay. You will. There's a good chance that you might work it out like quadratic equation is perfectly fine. It will work out fine. But there's a trick that take a square root immediately. And remember, these are our magnitudes, which is the positive square root we take. So the moment you take the square root, x squared becomes x, d minus x squared becomes d minus x, and it becomes a linear equation. K can cancel, so that is square root of k, square root of plus 1.00 microcoulomb is what? Microcoulomb is the unit divided by x. And then the square root of k, square root of plus 4.00 micro, and 10 raised to minus 6, divided by d minus x. Micro cancels out, k cancels out, square root of 1 is 1 itself. So 1 divided by x is more significant here. Plus square root of 4 is equal to 2.00 divided by d minus x. So that equation is significantly easier and less error prone than if you work without taking the square root, which would have led to a quadratic equation, but still not a very bad one. It saves you a little effort. So that's d minus x. And this is 2.00 x. This is 1.00. Take it to the other side. This is 3.00 x. So x is equal to whatever d was divided by 3.00. D was 1 meter, that's 1/3 of a meter. If it was 3 meters, it's 1 meter, and so on. So idea is the big challenge here is to figure out which side it is, and after that point, algebra is typically not that challenge. Questions? Yes.
So, into offset charges. We have negative numbers, we think you use that.
Oh, magnitude, not its magnitude.
So it's not, oh,
A magnitude. So the equation goes through. And so good question there is that what happens is that if they're oppositely charged, there are two regions where they can balance out. Here it was easy to draw this. It was easy that this is not going to work out. And it's going to be only one region that is a possibility. When you're doing positive and negative, at least in the initial thought, you would argue that there are two possibilities. But then there is a second argument that comes in. So let's say this was +1 and minus +4. A little bit. So this is +1 microcoulomb Q1, and this is -4 microcoulomb, that's Q2. Here, the electric field will be in this direction, E1. This will be in this direction. This cannot balance. That's not possible. On this side, if you use just the arrow as your measure, this will be E1 and E2 will be here. Sorry, E2 will be here. And it seems like it can balance on this side. But let's go to the third one first, and then come back. So here, this is E1, and that's E2. Now notice, I'm not worried about the lengths here. E1 is smaller in charge, relatively speaking, and it is farther. So in both charge and distance, it loses. So this will be significantly smaller compared to this. So this will be like this, and this will be like this. You would think that, oh, what if I go closer, if you go closer, this is getting even bigger. This is getting bigger, but not significantly. So one has to realize that this will never be able to beat this on the right side. That's because this is smaller in charge relatively and it is farther. Distance wise, it doesn't get an advantage. Charge wise, it doesn't have an advantage. So either way, there is no way this can beat this. Is that clear?
Yeah, but how would it, change that when you set the equal to each other?
Okay, I'll come to that. Okay, from that point on, that's not that bad. First, is that argument clear? That this cannot be? Or if you don't get it, as far as examples, if you're modeling, if you're saving your planet because of this charge problem, it doesn't help, but the key is that it's always closer to the smaller charge. If you get these two options, the zero field is always closer to the smaller charge. If there is ever you're confused, that's a key you can keep. Unless I ask you for the reasoning for that. So now you argue that this also is not possible. So that's only here. So that's your x, and that's your b. And now you again do the same thing. V1 magnitude has to equal magnitude of 2. And E1 now is k times Q1 divided by x squared. A magnitude of Q1. This is k times magnitude of Q2 divided by d plus x squared. That's the difference. I did that become plus there. Everything else is the same. Plus one. This cancels out. The microcoulomb cancels out. And what you will arrive at is plus 1.00 over x. This is equal to plus 4.00 square root of that divided by d plus x. And that is, let's say, 2, right? That's 1.00, 3.00. Is that clear? Okay, and from that, it's the same algebra, or it's very simple algebra. Yeah. But a key point in this was to argue that this is not, this is 0. That plays an important role in that. So make sure you understand why this region, it is 0 in that region. Why can't you have it in that region? That could be a conflict. Any questions? Okay. An electron enters the region of a uniform electric field E with a speed of 4 × 10⁻⁻6 meters per second. The horizontal distance of the plate is x equal to 5 centimeters, and the beam gets deflected vertically by a distance y. This problem has been designed in such a way that electric field, whatever that electric field is, acts like there is an acceleration in the y direction, either positive or negative. There is an acceleration, and from that point on, you can use ideas of projectile motion. If you were to throw a ball in the air under gravity, it falls down, and except that the numbers of the effect is from a different source. Gravity is an electric effect, but otherwise the ideas are very much the same. So there is a electric field of 2. So remember, force is equal to charge times electric field. I'm not using vectors. It is I'm just using magnitude. F is mass times acceleration. That's Q times C. So the moment you have an electric field, a massive charge with a charge Q experiences the following acceleration. That's the key. If you had a charge and a mass in an electric field, it experiences an acceleration of this. Like if you have a mass in gravity, we say that it is mass times gravity. But now since there is a charge, it is a charge that is interacting with the electric field. But the force is equal to mass times acceleration. Effectively, the acceleration is Q over n times E. So first go ahead and calculate the acceleration. From that point on, it is kinematics. Like just get the acceleration first and then treat it like acceleration. So this is charge Q, which is an electron. So it is 1.6 into 10 raised to minus 19 divided by mass, which is 9.1 into 10 raised to minus 1, and the electric field is given to be 2 into 10 raised to 3. So that comes out to be voltage plus 1.6 into 2. That's 0.35 into that goes up, so it's 10 raised to 12 plus 10 raised to 15. And this is the acceleration, so it is meters per second square. That's 3.5 into 10 raised to 14 meters per second square. If you remember, acceleration due to gravity on our Earth is 9.8 meters per second square on Earth. But this is an electron inside an atom, which is really tiny. Its mass is very tiny, so the effect is very different there. So it is very, we don't have too much intuition for that, but that's the idea that if you work on the problems and you get an intuition, at least at an abstract sense, is not by really feeling. That's the acceleration, and now we have to talk about what happens to the charge as it is moving. So we have two plates. The idea is that there is an acceleration downward. Initially, it has a velocity in this direction. That's your initial velocity. It starts accelerating only when the electric field is there. Electric field is there only between the plates. At least it drops down very quickly. So it comes in. And usually it's not one charge, there's a beam of charges. By beam, I mean there are many charges going in, but let's effectively think of one charge. And the moment it experiences here, it starts accelerating. So it starts going down. It's not accelerating horizontally. So acceleration A is 0 in the I direction minus A of that number in the J direction. That's your 3.5 into 10 raised to 14 meters per second square. In kinematics, x direction and y direction, this is uniform velocity, no acceleration, but x direction. That's time taken to go from here to there, let's say, here. That's your final point. That's your initial point. Time taken, delta x, that's your delta x here. The initial, that's given to you, I suppose, 4 into 10 raised to 6. And delta x is 5 centimeters, which is 5.0 into 10 raised to minus 2 meters. So two things given to you, you can immediately calculate delta t. But let's write down all the other quantities. Delta t, delta y is this distance. And the initial in the y direction, the final in the y direction, and acceleration. Acceleration is minus 3.5 into 10 raised to 14 meters per second square. The initial in the y direction, it is going horizontally, so that's 0. And we are looking for delta y, calculate the deflection y in centimeters, okay? Whatever answer we will get will be meters converted into centimeters. Notice that usually in these kind of problems, where there is uniform acceleration, you need three quantities in here, but we could decide for only two of them. But the main idea is on the x direction, you can calculate delta t, calculate this, but it's exactly the same amount of time. The amount of time it takes to go horizontally is exactly the amount of time it takes to deflect in the y direction. So calculate delta t and substitute it in there. We have done a lot of these problems earlier, but let's quickly do this. So the initial x is equal to delta x over delta t. So that's 5.0 into 10 raised to minus 2 is equal to, no. So this is 4.0 into 10 raised to 6 meters per second is 5.0 into 10 raised to minus 2 divided by delta t. That gives you delta t as this divided by this, 5 divided by 4 is 1.25, so 1.3, and in 10 raised to minus 8 seconds. That's the difference, even though the acceleration is small, but action for it, as it happens, is very small. We're talking in terms of very small numbers. So delta t is given now. We have to, so this is known. So that's 1.3 into 10 raised to minus 8 seconds. We are interested in delta y. This seems to be the missing variable. Since that's the missing variable, look for an equation that does not have the final, and that is delta y is equal to the initial y times delta t plus half a delta t squared. Delta y is what we're looking for. The initial y is 0 plus half times acceleration is minus 3.5 into 10 raised to 14. Delta t is 1.3 into 10 raised to minus 8 squared. Because when you square such a small number, it gets even smaller. 10 raised to minus 8 becomes 10 raised to minus 16, and that's minus of, okay. And that's 2.3 into 10 raised to 16, that's 10 raised to minus 2 meters. But we are looking for it and in centimeters, that's 2.3 centimeters. So tiny bit, 2.3 centimeters is pretty much like half of your thumb. I think I'll stop here. 2 more questions. Hopefully. Thank you.